So hello, general ideas. Today I'm going to go through last year's final, try to explain what was on it, what other things could be on it, going through. This PowerPoint that I have open right now is the final exam review one. I'm not going to go through this entire PowerPoint. I did yesterday, but just we'll comment a few things from it once again. The first one being the final is December 14th at 5:30. It's 5:30 to 7:30, so I'm going to leave it open to 7:45 so you can upload. Don't forget you must do questions 1 through 4 and then 4 of the last 5 problems. As I said, I covered this last time. I'm not going to bother covering it again. So I'm going to start here. And what I'm going to try to do is just go through what type of stuff you can expect to see. I'm going to go through what was on it and what could be on it. I don't know if an hour is long enough for me to do all 9 problems. I'm going to do as many as I can, and we'll see what we can do. I might be able to do all 9. So the first problem will be from chapter 28. 28 could be double slit, single slit, thin film, diffraction grating, polarization. Basically on everything on the left side of that PowerPoint that's up there. And so let's see what I asked. I said, orange light with a wavelength of 615 nanometers is incident on 2 slits. Okay, 2 slits, double slit, we know that much. Of width 0.04 millimeters, separated by 0.15 millimeters. The screen is placed 1.25 meters away. What is the distance from the center to the first dark spot? Okay, so this is double slit. We know it's double slit because they said 2 slits. And we want a dark spot. So I'll just take the equation as written up on the upper left side of the screen, that the distance for the dark is going to be YLD over M plus a half. And I'll say, okay, I want to find the position of the dark spot. That's Y. So I'm just going to be plugging straight into this. And I'm going to say, okay, lambda. Lambda is the wavelength. The wavelength was 615 nanometers, or 615 times 10 to the negative 9 meters. L. L is the distance from the slits to the screen. It's how far away it is. And so I say, distance from slits to the screen. Well, a screen is placed 1.25 meters away. That's L. D. D is the distance between slits. Now, I gave the width of each slit, though 0.04 millimeters, but that doesn't matter. What D is the distance between them. They're separated by 0.15 millimeters. That means 0.15 millimeters is D. And then I got that M plus a half. But it's just the first dark spot. The first dark spot happens when M equals 0. And so that's my equation. I just plug in and get an answer. And that's all there is to it. Part B. One of the slits is covered so light passes through a single slit. And once again, I gave the width of the single slit a second time. What is the distance from the center to the first dark spot? Well, for a single slit, we don't really have a quick equation to the distance. Instead, we have an angle. We know the sine of theta dark equals m lambda over a. Now, for single slit, m can't be 0. If m equals 0, this whole thing is 0. So for a single slit, the first one's going to be when m equals 1. This was the biggest trick on this problem that messed with people. A bunch of people used m equals 1 up here also. Keep that in mind. M cannot be 1. Or m can be 1. No, wait, single slit. M cannot be 1 for a single slit. I misspoke. But if m is 1, that just goes away. And so that means theta for dark is the inverse sine of lambda, 615 times 10 negative 9 meters, over a. Well, a is the width of the slit, 0.04 times 10 to negative 3 meters. This is a negative 1. It looks like a 7, but it's a negative 1. And that'll give me an angle. The thing is, I don't give a shit what the angle is. I said, where is that spot? And for that, we're going to use the fact that tangent of theta equals y over L. That means y equals L tangent of theta. Now let's use the same number as before, 1.25 meters times the tangent of 0.880957 degrees. And that's what I did last time. Now, obviously, I don't do the same problems. So, other things you can expect to see. Thin films. Keep in mind the thin films, the equations, which one's which, depends on how many times there's a phase change. But there's the equations for constructive and destructive interference. I could also put diffraction gratings on there. I could also put polarization. Polarization, if it's on there, would be a part of a problem. I can't make an entire problem. That's too quick. Thin films could be an entire problem. Diffraction grating, no, I'd probably work diffraction grating into part of a problem too. Or I could use one of the other of double slit or single slit with something. Questions there?
I'm good.
The second problem will be about relativity. Oops, that didn't do what I wanted to do. All of this noise. I could do a lot of things here, but it will probably be length and time elongation. Okay, there's three things you're going to see. Length changing, time changing, or adding vectors, or a combination of those three. I am not going to put on the relativistic energy stuff. And so last time what I said is in the short-lived TV show Firefly, the spaceship Serenity could travel at a speed of 0.276 C. The ship is 82 meters long, could fly for 14 days without needing to stop and refuel. Side note, literally the amount of research I do to write some of these problems is stupid. But people have worked out how long the ship could go before refueling because it's in some episodes. So, Serenity's crew measures 14 days has passed. How much time has passed for a stationary observer? Okay. The hardest bit of these problems is knowing what is proper time and what is time. Likewise, what is length and what is proper length. And for vectors, just knowing which one's u, v, and u prime. So here's the idea. This is time elongation. We're asking how much time passed. So at least we know which equation it is. It's going to be that delta t, I don't always bother with my deltas, but delta t equals t prime gamma. Right? Am I saying that right? Oh, gamma delta t prime. Well, gamma is the square root, one divided by the square root of 1 minus v squared over c squared. Now, proper time is the moving reference frame. If the people on the ship are moving and they say it's 14 days, that means 14 days is proper time. Now, note we should in time, we always work in seconds and all the SI stuff. For these, really, just use whatever units I give you and you give the answer in those units. So if it's 14 days for them, that's T proper. I want to solve for T. Let's just solve for gamma, just because I can. So V is 0.276C, so 0.276C. And that's going to get squared over C squared. That becomes 1 minus 0.276 squared is 0.076176 C squared over C squared. This allows my C squareds to cancel. It's going to be 1 over the square root of 1 minus 0.076176, which I'm just going to do that all in one step. That ends up being 1.04041. That's my gamma. So T is just gamma times proper time. And you get 14.6 days. But B, how long is the ship according to an observal? Okay, length of the ship is how long the ship is when it isn't moving. And I said how long the ship is. I said the ship is 82 meters long. I didn't say it's 82 meters long at some speed. I just said it is 82 meters long. So that's almost definitely the proper length. And I want L. Well, we know L equals L proper over gamma. And I already solved for gamma. I'm not going to bother solving for it again. And I'll get an answer. Now, the other thing I can do here would be vector addition. If I do vector addition, what to keep track of? V is the speed of the reference frame. U is the speed in a stationary reference frame. U prime is the speed of the object in the moving reference frame, which is moving at the speed V. That's the other thing I can throw on though. But this is the trick. Know what is proper length and time, know what is other length and time. Questions about relativity? The question after that will be from chapter 30. And chapter 30 has some of the most things I can do. Like, there's a lot there. It's normally gonna be some weird combination of them. I don't really have a good way of saying know how to do this bit. It's those equations. Know what all of those equations mean. Not all those equations work in all cases, and know how to deal with them. So this one says a gamma ray hits a stationary electron and deflects it. Okay, we have gamma ray, which is a type of light, hitting an electron. That's the photoelectric effect. No, sorry, that's a lie. That is not the photoelectric effect. That's Compton scattering. Compton scattering is the idea of a photon hitting an electron and bouncing. So a gamma ray, which is a piece of light, is a photon, hits an electron, that is Compton scattering. For Compton scattering, we know that the wavelength minus the initial wavelength will always be given as h over the mass of an electron times c, 1 minus the cosine of the angle. Now, I'd actually read what the problem said. What is the wavelength of the photon after deflection? Okay, that's just lambda. So that just means adding lambda naught to both sides. It's going to be lambda naught plus h over mec, 1 minus cosine of the angle. And so it would be the initial wavelength, 8 times 10 to negative 12 meters, plus h, which I assume I gave h. I did. 6.63 times 10 to negative 34th joule seconds, over the mass of an electron, 9.11 times 10 to negative 31st kilograms, times c, which I didn't actually give c. I assume people know it, though if you don't, I can always give it. I will be online during the exam. 1 minus the cosine, and I'm out of space. 1 minus the cosine of 23 degrees. I'm sorry, I cramped the end. And you just do that math. B, what's the energy of that photon? This will show up in some way, shape, or form, the energy of a photon. I'll make that, like, that's going to be on here somewhere. The energy of a photon is Planck's constant times frequency. The problem is, I don't know frequency. I know wavelength. But here's the other thing I know. For any wave, the velocity of a wave is wavelength times frequency. And for light, the velocity of the wave is c. And this means the wavelength, the frequency of a wave is c over lambda. And if I plug that into this equation, the energy of a wave is hc over the frequency, or over the lambda. I said my lambda backwards. Let's just try it again. That is how we'll get the energy. Times 3 times 10 to the 8th meters per second over 8.19 times 10 negative 12 meters. That is going to be 2.43 times 10 to the negative 14 joules. That will show up though no matter what I do with these problems. Energy is going to be important here. And C. Gamma rays can be created the same way as X-rays. Okay, if you see the word X-rays, you're probably looking at this right here. These were the equations for X-rays. What accelerating voltage do you need to create the initial wave? Yeah, that's the X-ray one. And so we'll say we want the accelerating voltage. I'm going to take that equation. I'm going to multiply, and it's lambda min. I'm just going to drop, I keep them in. So the lowest it can be, if you want to get it, the lowest, I'm going to multiply both sides by V, divide both sides by lambda. And just plug in. Charge on electron, 1.6, yep. And it said the initial. The initial lambda was 8 times 10 to the negative 12 meters. Am I still on the screen? I'm still on the screen. If I don't do this, which I probably won't do exactly the same, other things to look out for. Photoelectric effect. May ask about the cutoff frequency or cutoff wavelength or the work function. Make sure if I give you the work function, I'll probably give it an EV that you convert it to joules. I'd give the conversion factor. De Broglie wavelength may come up too, where the Broglie wavelength is just h over mv. Because de Broglie wavelength comes up, it's possible some classic physics can throw in, like just P equals mv. We're doing energy, so maybe kinetic energy is 1/2 mv squared, but I assume you remember that stuff from physics 1. But that's the general idea. It can be a weird combination of those things. Any questions on that chapter?
On Friday, when we go over practice problems, if I have like a question on a chapter or a different problem, can we just go over it then?
So Friday, when I finish the example problems, like the ones I plan on doing, yeah, I can do a different problem.
Sweet.
Let me go through the chapter 12 ones first.
Yeah, no, I'm certain that I'm going to have questions on some of those earlier chapters again once I start doing some more practice problems.
That's fine.
So
I'll happily do that. You can do that in my office hours, or as I said, after practice problems. I can normally stay till about 4:30.
Gotcha.
Okay. The next problem will be from chapter 12. And here's the good news about chapter 12. It has very few equations. And these equations look ugly as hell. But all of everything but the n squared in both of them are constants. And so no matter how ugly they look, they're really not that bad because it's all constants. And it says, What is the energy of an electron in the n equals 3 state of hydrogen? Okay. You know what? Fuck it. I'm going to do this on here. I don't even need to write it there. The energy is this. And I'm going to read ahead for a second. I give, at this point, just constants. Planck's constant, mass of an electron, charge on an electron, Coulomb's constant. And then I say, hint, you can get full credit without using all these constants. Here's the thing. I could plug in all these constants. I could plug in Me, Ke, E, and H. Or I could just know that that boils down to negative 13.6 EV over n squared. Now, if I plugged in all those constants, I would have got it in joules. And I actually accept it in joules or EV. But if I want to know the energy state, it's negative 13.6 EV over n squared, which in this case is, yeah, it's hard to write on there. I'll just go here. Which in this case is negative 13.6 EV over 3 squared. Or negative 1.51 EV. If you did put in all the constants, you would have got a negative 2.42 times 10 negative 19 joules if you did plug them all in. But I don't think a single person did that. I think everyone just wrote down 13.6 EV.
Give us the conversion, or yeah, the conversion for EV to joules.
I did not, because I accepted the answer in either way.
Gotcha.
If you gave it to me in EV, you got full credit. If you gave it to me in joules, you got full credit. Though, as I said, not a single person gave it to me in joules. No one plugged into that equation. But I would give credit for either one.
Dr. Lars, if we got something like this, which I don't know, we probably won't, but if we just did that nice big leap of logic to negative 13.6 EV without showing you where we got that
Full
from.
credit.
Full credit? Great.
That's why I said you can get full credit without using all these constants.
Yeah, there was something like that on the homework.
All right, yep, that'll work.
So what you're saying is I'll be daydreaming about a problem like this.
Yes, well, I'll talk about in a second what else I could do. Now, B. What is the radius? Well, there's my equation for radius. Radius is all of those constants times n squared. And when you plug in all those constants, you get 529 nanometers times n squared. That's what you get when you plug in all those constants. So it's just 0.0529 nanometers times 9. 0.476 nanometers. Once again, if you plug in all your numbers, I'll take it. If you don't and go straight to this, I'll take that too. And C. C was the one that actually messed people up on this problem. It says, if the electrons in the 3p subband, what are all possible states? Okay, 3p. What 3p means is n equals 3. And p, what p means is L equals 1. So it's definitely going to be 3, 1, and there'll be whatever my M of L and my M of S is all. And I say, okay, M of L can be everything from negative L to L. So if L is 1, that means my M of L can be negative 1, 0, or 1. And M of S is always a half or negative 1/2. And so all my possible states are going to be 3, 1, negative 1, negative 1/2. 3, 1, negative 1, 1/2. 3, 1, 0, negative 1/2. 3, 1, 0, 1/2. And 3, 1, 1, negative 1/2. And 3, 1, 1, half. And that's it. Know your SPDF that they stand for 0, 1, 2, 3? The other thing I could do here that isn't this is I could go for this equation instead. This equation also isn't very complicated, and I'll give you the Rydberg constant if you need it. So that's the other thing I could do, would be like, something goes from the 5th energy level to the 3rd. What is the wavelength? But even if I do that, it's not very complicated. The 4th problem will probably be the second easiest problem on this exam. I'll come back to what the easiest one will be when I get there. Any questions on that?
Nope.
After that, those are the 4 questions. You have to do all 4. After that, we get into the earlier stuff. The first problem will be, I give a bunch of point charges. And when I give a bunch of point charges, I either say, what is the electric field? Or what is the force? Or what is the voltage? Or what is the potential energy? Or some combination of them. Things to keep in mind. Force and electric field are vectors. Potential and potential energy are not. And so I say in this one, in the figure below, Q1 is -2 nanocoulombs, Q2 is 3 nanocoulombs, D is 0.5 meters. What is the electric field at point P? So that's electric field. Once again, electric field is a vector. And so I need to say what the electric field looks like. The electric field will point directly away from all positive charges and directly towards all negative charges. And so my electric field respectively would be a piece from E2 and a piece from E1. And I'll say for each one, I can work out what the value is. E1 will be KE Q1 over all squared. So it'd be 8.99 times 10 to the 9th. Which one was 1? 1 was the negative. 2 nanocoulombs. Now keep in mind when you do these, that negative sign, okay, for force and electric field, use absolute values. For potential and voltage, do not. That'll throw you off. But this negative sign is just direction. We're going to work out the direction separately. So I'm just going to say 2 nanocoulombs and just say use it for direction, which is 2 times 10 to the -9 coulombs. And D was 0.5 meters. Then I can get a value. E2 is just KEQ2 over R squared. Or KE, I'm not going to bother writing it again, times 3 times 10 to the -9 coulombs over 0.5 meters squared, which is 107.88 nanocoulombs. Now, if I want to add these fucking vectors, right, I'm going to have to take this E1 and say it's up and to the left. So I'm going to break this into 2 components. One directly to the left and one up, where the values will be my E1y and my E1x. So I can split those up. E1x equals E1 cosine theta. It's actually going to be negative because it's to the left. So it'll be 71.92 cosine of 60 degrees, which is 35.96. E1y equals E1 sine theta, or 71.92 sine of 60, 62.28. Then I'll say, okay, this total E's in X, my E is going to be E2 minus E1X, right minus left. 107.88 newtons per coulomb minus 35.96 newtons per coulomb, just because they're pointing in opposite direction. 71.92. In y, all I got is E1y. And so for magnitude and direction, magnitude would be the square root of EX squared plus EY squared. And so it would be the square root of this plus this. Which doing that math gives me 95.1. Just launch that pen. And direction will be the inverse tangent of y over x, or the inverse tangent of 62.28 over 71.92, which is lower on the page. This is a bit time consuming. I fully acknowledge this. I did the whole thing where I took the exam and timed it. I will say, I'm going to be honest, when I took the exam out for you guys, it wasn't fast enough. And I went back and changed problems to make it go faster, or make it go shorter. I'll try to make the numbers here kind of nice. This is a little time consuming as is. I'm going to try to make it not be this ugly. Okay, B. If a 4 nanocoulomb charge is placed at point P, what is the force it feels? Force equals QE. So it's just going to be 4 times 10 to the negative 9 coulombs times 95.1 newtons per coulomb, 3.81 times 10 to the negative 7 coulombs. Direction? Well, it's negative. So it's going to be the opposite direction. This was at 40.9 degrees. So it's going to be at 100 degrees off from that. If I remember correctly, someone just wrote opposite direction last time. I'm like, yeah, good enough. Without adding the 180. If I do voltage or potential energy instead, don't worry about vectors. Just do them and add them up. However, make sure you include the signs. Any questions there?
Nope.
Okay. The one after it is the one that the most people skipped last semester. And I kind of expect the most people to skip this semester too.
It's just time consuming.
Yeah, it's time consuming. But the last one was a Kirchhoff loop. Now, I've actually done this problem before with you guys. Fun story. The Kirchhoff loop I put on the first exam last year, I had a mistake in it. And so one of the currents came out to be 0, which confused the fuck out of the only person who got anywhere near a correct answer. So this was literally, I gave them the exact same problem again, but I fixed the numbers. And it says, what's the current through each of these resistors? Well, what's the current through resistor 1, 2, and 3? We're not going to worry about 4 because it's the same as 3. Time. Yeah. A part of me says, like, I just kind of want to skip it and make sure I cover everything, but I'll go through it a fast version. What you're going to have to do is start by predicting the current. I predicted that it's going to go up through 1 and then to the left, up through 3, and then to the right, up through 1 to the right, up through 3 and to the left, and then down through 2. Why I predicted that? I don't know. It made sense at the time. It doesn't matter if you're right or wrong when you make these predictions. You just guess. And so what I'll say is the current going from 1 and 3 go into the junction and go out at 2. That means I3 plus I1 equals I2. And then I'll make my loops. There are 3 possible loops. All this left loop, the right loop, and the big loop. And I'm going to pick 2 of them. I did the left loop last time, where I went up through all1, through V1, down through V2, through all2. That loop, sum of loop is always 0, will be up through all1, through V1, and I'm with it, so it's positive. Down V2, but I'm going backwards on V2, so I have to subtract it. And then through all2, and I'm still in the direction of my current. Then I did the left loop, but I did that one counterclockwise. Up through all3, through V3, down V2, through all2, through all4. Although actually I started at V2. I did V2, then all2, then all4, then all3, then V3. So starting at the middle top and then around. That loop. Down through V2. Actually, let's give myself some more space. So I'm going against the battery through all2, through all4, which also is the same cone as I3, through all3, through V3. Once again, if you're going from the small side to the big side of the battery, it's positive. Big side to the small side of the battery, it's negative. If you go with your current on a resistor, it's negative. If you go against the current resistor, it's positive. I could do the big loop too, but I'm not going to bother. I'll just say it out loud. It'll be negative all1 I1 plus V1 minus V3 plus all4 I3 plus all3 I3. And what I'm going to do is say each of these have I2 in it. So I'm going to solve for the other term. I'm going to add all1 I1 to both sides. And then divide both sides by all1. And you know what? I'm going to be lazy and plug in some numbers, and I'm just going to do that over here because I'm out of space. V1 is 13. V2, no, what? I haven't written there, is 3. Minus 10I2 over 5 is 10 minus 10I over 5, so it's 2 amps minus 2I2. This guy, they both had I2, so I'm going to solve for all 3. So I'm going to move both of these terms over. I'm going to factor out these O's and divide. And once again, I'm just going to plug in some numbers now to make my life less messy. I put that in different order. So it's 8 volts minus 3 volts minus 10 ohms I2 over 4 plus 3 is 3 plus 2. So that is going to be 1 amp. How is an amp an N? 1 amp minus 2 I2. I'm then going to take both of these and plug into this equation. 1 amp minus 2 I2 plus 2 amps minus 2 I2 equals I2. That is 3 amps minus 4 I2 equals I2. 3 amps equals 5 I2. Really? I got 3/5? Yeah, I got 3/5. I2 equals 0.6 amps. I'll then plug that in here. I1 equals 2 amps minus 0.6 times 2 is 1.2. And I'll plug it in here. 1 amp minus 1.2 amps equals negative 0.2 amps. And there's my answers. I1 is 0.8 amps, and it is up because it's positive and I guessed up and got it right. I2 is 0.6 amps, and it's down. It's down because I guessed down and it was positive and got it right. I3 is 0.2 amps and is down. It's down because I guessed up and got a negative answer, so it must be down. And those are my answers. Any questions there? Okay. I got 3 problems left and 10 minutes. Well, I can go straight to 2, 20 minutes. Okay. This problem has a story to it. There was a student who really wanted to make a railgun last semester, and we kind of worked out how it could be done throughout class. So he got a problem. So it says, to create a railgun, create the setup as shown. A current of 3 times 10 to the 5th amps is run along the rails with the direction as shown. The piece attaching the 2 rails, the armature, is free to slide. Assume the distance between the rails is 0.1 meter. Was the magnetic field in the middle of the armature at point P? So, magnetic field circles around a current carrying wire, following the right-hand rule. If you want to get the direction, you're going to point your thumb in the direction of current, and whichever way your hand curls is the direction. Now, if I look at from the top, when I come from the top, what I get is when I curl around, that says the magnetic field in between should be down into the page. When I go to the bottom and I do the right-hand rule, my fingers curl, I get the magnetic field should be down into the page. And so the magnetic field is just going to be the one from the upper piece plus the one from the lower piece. But really, they're both the same distance away, and they both have the same current. So it's just going to be twice the B of one of the two. Now, magnetic field from a current carrying wire is mu naught I over 2 pi r. But in this case, we're going to multiply by 2. So I'm just going to kind of kill that 2. And say the magnetic field is into the page and is 4 pi times 10 to the negative 7. I forget the units of that. Tesla meter per amp. Times the current. 3 times 10 to the 5th amps. Over pi times r. Well, r is the distance to that point. They're 0.1 meter away from each other, so it is 0.05 meters because it's in the middle. And it's 2.4 Teslas into the page. Next bit. What force is acting on the armature? Well, the armature is a current carrying wire. And the force on a current carrying wire is ILB sine theta. Now, in this case, theta is 90 degrees because the magnetic field's into the page and the armature is down. And so it'll just be the current times the length times B. Now, direction, that's right-hand rule. You put your hand in the direction of the current, which is down, and you curl your fingers in the direction of the magnetic field, which is into the page, and your thumb points in the direction. So the direction of the force is this way, and it's to the right. C, since the armature moves, the area of the loop increases, causing an induced magnetic field. What direction is the induced magnetic field? So I didn't actually do the math here, I just asked for the direction. Okay, the flux is getting bigger. If the flux is getting bigger, it wants to reduce the flux. Flux is getting bigger because the area is getting bigger. If the area is getting bigger, flux goes up. So we want to reduce the flux. That means we want to be in the opposite direction of the magnetic field we have now because we want to reduce it. And so it's going to be out of the page. The induced magnetic field is going to be out of the page to reverse it. Now, things I could do differently. I could do more with induced magnetic fields. I could actually have you solve the equation for induced magnetic fields. I could do the charge of the charged particle, F equals QVB sine theta. But almost definitely something about induced magnetic fields would be there, as well as something about the magnetic field from a wire or maybe a loop or a solenoid. Questions there? Problem 8 will be a OLC AC circuit. That's what it's going to be. Things I could do differently is I might include phase angle, I might not. I might include resonant frequency, I might not. I might include average power, it's IRMS, VRMS, cosine phi, I might not. But let's do it last time. Bandpass filter, device that passes frequencies within a certain range and reflects all frequencies outside that range. Let's say an RLC circuit with that resistance in a series with that inductor and that capacitor. What is the resonant frequency? So guys, because of time, I'm going to go a little faster with these. I'm not going to bother writing in every one of the numbers. If you want to see these steps individually, these solutions all posted online with the numbers written in, or just send me an email and I can show you. But if I want resonant frequency, I'll just plug into that equation and solve and get an answer. As I said, I'm going to kind of skip plugging it in just for time reasons. B, if the frequency is 12 hertz, what's the impedance? If you want to get impedance, impedance is the square root of R squared plus x of L minus x of C squared. Anything with impedance, you need to get x of L and x of C. Well, x of L is 2 pi FL, and x of C is 1 over 2 pi FC. Now here I gave the frequency. I said it's 12 hertz. And so I'll just plug into these. I'll say 2 pi FL, so 2 pi times 12 times 200. 1 over x this. So I say 1 divided by 2 pi times 12 times 5 to the negative 6. And I can plug those into here. C, what's the phase angle? Phase angle is the inverse tangent of x of L minus x of C over all. Once again, I skipped showing my work of plugging in the numbers. It's just plug and chug though. There's no real solving though. If I do something else with this, I may say, hey, this is the RMS, what's the max for current or potential? Or I could say, if I'm mean, I could say, is this phase angle mean, is the voltage leading or lagging? That is kind of mean of me though. Or I could do something with power. Or I might include Ohm's law. Don't forget that VRMS equals IRMS Z, which isn't actually written on this slide anywhere, because this is V equals IR. But I could include that also. This can be a time-consuming problem because of all the steps, but it's usually pretty simple. It's plug and chug. Any questions? The last problem will probably be the easiest one. It wasn't exam 2, it probably will be here now. The last problem will involve lenses and mirrors, where the equations for lenses and mirrors are these guys. And what I did it about was the lens in Cyclops' visor. And I said Cyclops from the X-Men has a visor with a ruby quartz lens that focuses I-beam. This visor was a converging lens of focal length of 1.4 centimeters. Okay, this is a lens problem. Now, if it's lens or mirror, it's the same equations. If it's a mirror, the only difference is that the focal length is half the radius. And I say if it's a converging lens, that means the focal length is positive. If it's a diverging lens, I'll probably say of magnitude something, but don't forget if it's a diverging lens to make it negative. That is important. And so we're saying the focal length is 0.014 meters. And I say, and it sits 1.5 meters away from his eye. How far away from the lens would his eye beam be focused? That means P is at 1.5 centimeters. And 1 over P plus 1 over Q equals 1 over F. That means 1 over Q equals 1 over F minus 1 over P. Or 1 over 0.014. I said I wasn't going to plug in numbers, and here I am doing it. But that's not Q, that's 1 over Q. So Q is 1 over that, and Q is 0.210 meters. And so it's 21 centimeters away. Is it real or virtual? That's a positive number. If that's a positive number, real. If Q is negative, it's virtual. What's the magnification? What was P again? 0.015. Is it inverted or upright? It's inverted. I know it's inverted because that's a negative number. It's magnified. It's bigger. It's 14 times bigger. And that's the idea. Things I could change here is make it a diverging lens. If I make it a diverging lens, though, nothing really changes other than Q is negative. Sorry, that's a lie. Take that back. I didn't change it except F is negative. Or I could go and make it a mirror. If I make it a mirror, you just got to remember that all F is all over 2, where it's positive for a converging mirror and negative for a diverging mirror, or positive for a concave, diverging for a convex. I have to think of it like concave. It's like a cave. That's converging. That is last semester's exam, or last year's exam. I didn't teach this class last semester. That's the type of stuff you can expect, and those are my hints for doing it. Any questions in general? So I only got like 7 minutes to my office hours begin.
I don't really know.
Okay.
I'm
Well, I'm
probably
gonna
gonna keep the trend going of the
say again.
Kirchhoff loop, just saying, "Fuck it, I'm not doing it." You know.
I mean, it's also the most annoying problem to grade, so I'm completely okay with that.
Yeah, it's not that it's conceptually hard, it's just very time consuming, and the little mistakes of the stress during the exam or
Yep.
the time, it's just like,
I don't blame you. It is perfectly okay. That's why you're allowed to skip one. Someone did actually skip problem 9. Of the 6 people who took it, 5 people skipped the Kirchhoff loop. 1 person skipped problem 9. And I'm like, really? That one? You skipped that one?
yeah.
But all right, we're gonna stop there.
All
Have
right.
a good day. And tomorrow we'll do practice problems for chapter 12, not chapter 12, chapter 31. And hopefully this was helpful. Bye.